So, what we will talk now is the electrical design of the battery pack. So, out of the 4 design aspects, electrical design, mechanical design, thermal design, BMS and firmware. Now, we will start with the electrical design of the battery pack. So, type of cell and the hierarchy of a battery pack. What are the type of cells which you have already studied in the past chapters? Again, just for understanding, there are 3 different type of cells we use: prismatic, cylindrical and pouch. So, any of the battery lithium ion battery pack, you see only these 3 form factors are available. Either it could be a prismatic, or it could be a cylindrical, or it could be a pouch cell. So, using any of these cells, what we do? We make modules. These modules are generally low voltage module, smaller in weight, and then combining all these modules together, we make a pack. The last video what I have shown you, there was 2 modules. So, the cell is the basic unit of lithium ion battery pack. So, a cell will tell you its voltage, current capacity. Using NPTEL-NOC theory, you club together these cells in parallel and series combination and you make the modules. Then generally you make modules in club modules in series generally most of the time to make a battery pack. So, a group of cells assembled together either in parallel or in series or in both makes a module, and then when you club all the modules together becomes pack. Now, making modules from the cells, how do you make a module from the cells? Now, you have a cell, prismatic cells here, which dimensions are provided: height, breadth and the thickness. You also have identification of what is the positive terminal, what is the negative terminal. And then if you see, you have all other information required. The voltage, nominal voltage of this cell is 3.65 volt, capacity is 14 Ah. That means 1 C charge and discharge can happen at 14 ampere. Length, breadth and height is given. If I have to increase the capacity, what I have to do? If I have to increase the capacity, what I have to do? I have to keep the cells in parallel. So, if I wanted to make a 120 Ah battery pack, so let us consider this instead of 14 Ah, consider this as a 15 Ah cells here. So, if I have to make the cells in parallel, if I have to make a capacity of 120 watt ampere hour, if I have to make a pack of 120 ampere hour, so what I have to do? 120 hour divided by this 14 Ah. So, that many cells would be in the series. So, here it is not 15, it is basically, this is basically here 14 Ah. So, 14 into 8 how much? 112. So, this becomes 112 Ah. Now, if I want the pack voltage to be the module voltage to be 29.2 volt, what I have to do? Now, you divide whatever voltage you require by the nominal voltage of the cells. So, you require 8 numbers of cells to reach to 29 volt. So, if I require 112 Ah and 29.2 volt modules, what I have to do? I have to take 8 cells in parallel first. What we follow is parallel first, series second. So, that is why NPNS. So, parallel first, series second. So, if I have to make a 112 Ah 29.2 volt battery pack or module, I say module. So, what I have to do? I have to put 8 cells in parallel first, then each of the 8 cells 8 times in series. So, how many cells total will have? 64 cells will have together, and that will become one module, which will give us a battery pack capacity of 112 Ah at the rate of 29.2 volt. Now, you can make it at any. Now, if I wanted to make 48 Ah or 56 Ah, let us suppose I have to make a battery pack which requires 46 Ah, sorry 56 Ah. What I have to do? I have to make 4 numbers of these cells in parallel, but what would be the voltage at that time? It would be 3.6 volt. Now, I wanted to increase the voltage to let us suppose 7.2 or 7.3 volt. So, I have to make 2 numbers in series. So, that become 8P2S. Similar way, if I wanted to make 48 volt nominal capacity, how many cells in series? 13 numbers of cells in series. If I have to make 51.2 volt, how many cells in series? 14 numbers of cells in series. But if I wanted to make 112 Ah and the 51.2 volt, then what happened? 8P and then 14 in series. So, 8P module becomes now one cell, even though it is a combination of cells of 8 in parallel. So, now it is considered as one cell of 112 Ah. So, this is how we make modules from the cells. So, we have to define how many modules we require. So, for 60 volt, if I have to make a 60 volt battery pack, I can go with the 2 modules of 29.2 volts. Again, EH also need to be defined, then only you would require, that is what would be the length and width from this dimension of the cells. Now, assembling modules to make pack. So, what we have done, that we have made 2 modules. Now, we assemble both the modules in series to get the required capacity of voltage as well as current. Once we have made these modules, the bus bar is attached. So, each cells, now it is 2P configuration, 2P16S configuration. So, in this we have 2P in 8S, here again we have 2P 8S. Now, these both are connected into the series. Now, once both are connected into the series, now it becomes 2P16S. Now, 1C rate or 1C charge or discharge rate of this pack would be what? It would be 14 Ah is for one cell. So, 2 cells are in parallel. So, my charge and discharge capacity for 1C rate becomes 28 Ah. So, each cell, now here it is a one cell, we have first cells here, second parallel cells here, both the cells together is sending 14 ampere, 14 ampere. So, total current becomes 28 ampere. So, 1C rating of this pack is 28 ampere. Then in the series it is going to the battery 14 ampere, again in the next it will come out 28 ampere together, 14 plus 14. So, the current through bus bar is at 1C rate is 28 ampere. Now, each module, this one module together, sorry, this one collection of 2P cells is a 3.6. Each module is 29.2 volt with the 28 Ah capacity. Both the modules together in series gives me 58.4 volt. So, now my battery pack is made here. This battery pack capacity is 28 Ah and 58.4 volt. If I talk about capacity in terms of energy, then it would be approximately 1.65 kilowatt hour. Once we have done that, then we assemble. The similar video, first module ready, second module is ready. We are putting all other mechanical design constraints in plate, base plate, tie rod, then external casing and get assembled as a battery pack. Now, what are the issues need to be addressed in a bus bar? The first one is least resistance to the current flow. The second thing comes, because if your resistance is high, what will happen? Your power delivery will not be efficient. Your bus bar will get heated up. Since resistance you cannot make 0, you can go down as much as possible by selecting a proper material, designing a proper bus bar. There would always be some resistance, and when there is a resistance and the current is flowing through that, there would always be heating. So, you have to worry about, with the designed current flow, what could be the maximum temperature rise, and once you know what could be the maximum temperature rise, and if it is acceptable, well and good. If it is not acceptable, you will go back, you will change the design of the bus bar, so that your temperature rise should not go beyond the designed limit. When I say designed limit, generally it is supposed to be ambient plus 10 degree, not more than that. It should be able to handle the short circuit current stresses and the protection. What are the things we use for protection? If I do not have a BMS, let us suppose, what are the things I can use? I can use electrical fuse, I can use PTC devices, or I say PTC material, positive temperature coefficient. So, when the temperature keeps on rising, resistance keeps on rising, at some particular limit you will not have any more flow of current. So, at least other parts get, and that part is kept somewhere where you can maintain the temperature and other things without much problem. So, such type of devices we say PTC, positive temperature coefficient devices or materials. The another thing is thermal fuses. In fact, electrical fuses also work on the thermal concept only, but thermal fuses, as soon as you take out current more than the designed limit, it will open up because of the change of the shape. So, temperature keeps on increasing, because of that it keeps on changing the shape and that contact points gets opened up. This is one type of thermal fuse. Another type of thermal fuse, it will melt. So, now there is no more current. Then EMI EMC noise suppression. When you are designing, you have to design in such a way that it should not impact the nearby electronics components, or to you even. A lot of people, the heart rate is susceptible for EMC EMI noise. It should not affect the human, it should not affect the nearby electronics. There are various joining methods. What would be the best suitable method for my design? Why bus bar design is so important? We can just tag here and there and can still get our battery pack working. So, I will say you what it can happen if you do not design it properly. If you do not design it properly, your battery pack may not work at all. Now, if your requirement is take out 30 ampere or 28 ampere current and you have designed for 10 ampere current, what will happen? As soon as you exceed from the 10 ampere current, something goes wrong and your battery pack is useless. Efficiency, we have talked something parallel path. If the resistance is not same in all the paths, what happens? Wherever the, if you see this one, least resistance to the current flow, wherever the least resistance would be there, more current will flow in that path. If more current will flow in that path, more heating will take place, because heating is the function of I square. Your efficiency will come down. If you have a single path and you have not designed the bus bar properly, it would lead to again more heating, less efficiency. You are wasting heat, you are wasting energy, and then to manage that heat, again you are drawing the current from or energy from the same battery pack. its overheat self and also nearby components. What are the nearby components? It is cell or some insulation compression material, or its electronics like BMS, or it's like harness, sensors and other thing, and everything works within some limited temperature range. It could be 70 degree, it could be 50 degree, it could be 20 degree, but the temperature is beyond that, it won't function. And if you keep on heating because of your inefficient bus bar design, it's anyway getting heated up, but then it's also hitting the nearby components. So, other than the loss of efficiency, you are also losing the functionality of the pack. If all such things happen, if your particular sensor where that heating is happening and stop functioning, what will happen? Or not functioning properly, functioning erratically, what will happen? Your safety is compromised, your protection is compromised. So, these are the things can happen if you do not design the bus bar. So, that is why bus bar design is very important. At the end, because of the overheating, local melting or non-functioning or erratic functioning of the sensor, the whole pack can get damaged, can lead to the safety event. There could be complete structural damage. It is not only structural damage, it could be fatal to even passengers, human nearby. So, what are the things required for electrical design of the battery pack? The first one is bus bar design. When I say bus bar design, what are the important aspects of bus bar design? It is a conductor material selection. You always try to select a conductor which has the least resistance to the current flow, or its resistivity is minimum. The other things also comes in picture, like mechanical strength, thermal strength, all those things also comes into the picture. But the first and most important factor is how can you reduce the resistivity, or do you have a material which has least resistivity. Then design criteria, what are the things you are setting up, that my current flow should be this much, it should not go beyond this temperature. Thermal consideration, see every material, the resistivity changes with the temperature, and it also has a limit at which temperature it can function best. Then it has the safety limit, that beyond this temperature something can go wrong. So, all those things need to be taken care during the thermal consideration. Short circuit scenarios, huge current flow, how can we reduce, how can we mitigate if there is supposed to have any failure and other thing. Mechanical consideration, my structure is safe or not, my bus bar when I am putting is able to take all those thermal, resistivity, other design aspects, limits and still rigid. Insulation, a direct touch can lead to severe problem. Insulation is also required, that it should not touch anything else, any other conductive path. It is also required for EMC, EMI noise, to suppress those EMC, EMI noise. And when you have considered all those things, then you need to optimize, because it is a material, it is a cost. So, you have to optimize the design with the least amount of material, you can get the maximum output of the power flow. The second issues which we have to worry about is contact resistance. Wherever two surfaces overlaps or get joined, the contact resistance comes into the picture. It is not the material resistance, it is the interfacial resistance, and you cannot have an infinite length of bus bar or a design which can take care of joining all the cells together. So, here and there you need to keep on joining. like a voltage sensor goes over the bus bar. Either you can weld at one point or you can weld at the multiple point. You cannot fuse it together. It is not the same material. Even the material is the same, but it is not the same infused material. It is two different surfaces. So, there would be some contact resistance always. So, you have to reduce this contact resistance, because as soon as there is word resistance, that is what we are talking about from that time. We try to minimize the resistance. So, we have to minimize the contact resistance also, otherwise it would lead to all those same problems: heating up, local melting, local deformation, failure of the component, and we have been facing these issues on regular basis in our battery pack. Then the voltage drop. See what happens, lithium ion cells, it can run anything between 3 volt to 4.2, 4.3 volt. Now, at the higher side, even a 0.1 volt drop can bring the SOC by 8 to 10%. If I have higher resistance, other than the problem of heating, self heating, damaging and structure, it would also tend to reduce the voltages. And as soon as my voltage get reduced because of the resistance or voltage get dropped, my whole SOC will come down. So, the resistance when I am talking about list resistance, it also helps to reduce the voltage drop, but there would be a resistance, there would be a voltage drop. So, we need to find out what could be the voltage drop in such cases, and based upon that we calculate all other parameters like SOC, SOH and all those things depending upon this voltage drop. Current equalization. It is impossible to get the whole current through one single path because of the huge current demand. It is not our home system where we have 5 ampere or 15 ampere maximum requirement. It starts from that point. It can go hundreds of amperes. Even for a smaller vehicle, it can go for 30 ampere, 40 ampere, 50 ampere. So, it leads to design multiple paths, but then in each path the current should be equal. There are various joining methods. Welding is one part, the mechanical joining is another part. So, we have to look upon which works best for our design, which can mitigate all those things: voltage drop, contact resistance, the full conductor resistance all together. How do we select a conductor? So, the first thing comes bus bar material selection, then we have to worry about thermal consideration. Once we have done that, then we have to find the characteristics of the bus bar material. The material selection is critical for electrical performance, should have a great mechanical rigidity, should help in functional safety. Thermal consideration, when I talk about thermal consideration, it should have a sufficient ventilated space, so that any excess heat generated during the power delivery can be taken away. First of all, there should not be excess heat, but if somehow during your design itself you are encountering excess heat, you also need to worry about how it can be vented. A characteristic of a bus bar material, it should have low electrical and thermal resistance both, because if you do not have low thermal resistance, it will not be able to vent out its excess heat. It should have high mechanical strength both in tension, compression and the shear, because the whole battery pack, when it moves, you find all types of forces acting on that: tension force, compression force, shear. High resistance to the fatigue failures. When I say fatigue, it is basically a cyclic phenomenon, and when you are sit on the road, that cycle thing keeps on happening. Low electrical resistance to surface films. When you are selecting a material, it is always, all materials tend to form oxide layers. In some of the materials happen more, some of the materials it happens very less, but it happens. As soon as it comes in contact of air, there would be oxide layer formation. So, that layer formation should not hamper your current flow. It should not increase the resistance. It should be easy in fabrication, easily you can cut it easily, you can weld it easily, you can fold it easily, that means bend it easily. Generally it is open, in the sense you do not provide much of the insulation or covers in the battery pack. So, it should have a high resistance to the corrosion. Cost is important, least possible cost, so that your whole battery pack cost can be brought down. As of now, when you compare cost and other parameters, copper becomes best material. The next best material is aluminum, but aluminum has 61% lower conductivity than the copper. So, what you tend to do? You increase the thickness or the surface area, you increase it, and that helps in dissipating more heat. As soon as you are increasing the surface area and thickness, the overall resistance of the bus bar comes down, and it also helps you to get more thermal heat dissipation.